Good afternoon. We continue with the discussion on the stability considerations of the equilibrium points in a dynamical system. Now recall what we have extensively looked at is the case of linear systems, linear autonomous systems. We actually classified the type of stability, type of equilibrium point, the specific nature of the equilibrium point by looking at what is called the behavior of the characteristics in the neighborhood of the singular points or equilibrium points. Now this is a prelude to looking at nonlinear systems. In fact, there are many nonlinear equations that you come across for analysis, and one of the methods of studying nonlinear problems is to linearize it. That means you replace the problem by a linear problem which lies closer to it in some sense. You have seen this before. And then linear systems, you know a lot of things about it. Now if you can show that the behavior of the linear systems will hold in the case of nonlinear equations also, then you are done. And this is generally the strategy that one uses for this. I will tell more about it later, but we will look at a very specific example which is interesting. And this is of course the motion of a pendulum. Motion of a pendulum about its position of on a point of instability. Now, see, if you have a pendulum, suppose this is the pivot, and then in a pendulum usually hangs down like this. Usually hangs down like this, and there is the bob of the pendulum here. It just hangs down, and then what happens is, if you just push this is an equilibrium position, and if you push this, then you see it moves in this direction, and then it comes to this, and at that stage what happens, it just goes back, and you can see that unless some resistance works, the pendulum will go on and on, or it will execute what is called the simple harmonic motion. And therefore this vertical downwards position is an equilibrium point, which is a stable equilibrium. Okay, it's a stable equilibrium. Now what we are looking at is another equilibrium point. Another equilibrium point is when you keep it up vertically, there is certainly a point where it attains equilibrium. See, this is the pivot, that is vertically. But what happens with that equilibrium is that it is very unstable. Why? What happens? Suppose, see, there is a point where you can keep it in equilibrium. Whether you can do it or not, it's a different question. What happens is the slightest perturbation would make the pendulum to really take this path and come down and then attain this equilibrium. Now this is a stable equilibrium, this is an unstable equilibrium point. Now we look at the problem about the unstable equilibrium point. Okay, how to describe this? I will write down the equation which comes from physics. Okay. This vertical line upwards is considered as the baseline about which we look at the discussions. And then theta is the angle that the pendulum makes with this vertical line. So this is marked here as theta. Now what we want to work on is the following. Okay, what is the equation? The equation of motion is it's a nonlinear equation. Where theta is the variable, theta changes with time. Okay, so theta is a function of t given by theta double dot. Theta double dot is the second derivative of theta with respect to t plus 2k theta dot minus q sin theta. See, this equation is something that has been derived from physical considerations. The consideration of physical realities. This is purely the realm of physics. Now this is the second derivative of theta. This is first derivative of theta, and this term is the nonlinear term. Now this is the nonlinear term. Q sin theta is nonlinear. Okay, so this is not a linear equation, right? So here we assume Q is taken to be positive and K is also positive. These are the conditions. But we shall not bother how you came across this equation. This comes from physics. Now what we do is we linearize the problem. How do we linearize the problem? You see that the dependent variable is theta, or we are looking at how theta changes in the vicinity of the equilibrium point. You see that theta equal to 0 correspond to the equilibrium point for which the bob will be just vertically occupying the equilibrium position vertically up and not down, not the down one. Down one will correspond to pi. Okay. Now what happens here? If you look at this problem, then you see that for small values of theta, sin theta is approximately equal to theta. Okay, nearly equal to theta. Now what do? We look at this problem. So the equation, the approximate small theta is theta double dot plus theta dot minus q theta equal to 0. Now you can transform this into a system. What is the system that corresponds to it? The system that corresponds to it is d theta by dt theta dot and d theta dot by dt equal to minus 2k theta dot minus plus q theta. Okay, that is, this is the system that you have. Equal to, this is theta dot, so this is equal to 0, 1 minus 2k q. This case where you are assuming q is positive, k is positive. Now this system we have already looked at. This is the system that we have. So a equal to 0, b equal to 1, c equal to minus 2k, d equal to q. Now from what we have already discussed, you see that theta equal to 0, theta dot equal to 0, which corresponds to this equilibrium point. Okay, the upward equilibrium point, because we are taking this angle as theta. So when theta is 0, you are here. Now what about this eigenvalues of this? The eigenvalues of this corresponds to the roots of lambda square 2k lambda minus q equal to 0 and lambda equal to plus or minus minus 2k plus or minus root of so it will be, after simplification, it will be minus k plus or minus root of k square minus plus q. So you see that you have two, you see from this it is clear, we are assuming q is positive, k is positive. Now you see that this term, there are two values, lambda equal to minus k plus root of k square plus q, then it is positive. So that's a positive eigenvalue. And then you have a eigenvalue which corresponds to minus k minus square root of a square plus q. And this one, so lambda 1 now it's clearly this is positive. Lambda 1 is positive, lambda 2 is negative. Therefore, you have got two eigenvalues which are positive, one positive, the other one negative. So, this is so theta dot equal to 0, 0 is a saddle point. It's a saddle point and represents an unstable equilibrium. So which is the reality? If the bob is, you can balance it there, but you see that it is something which can be easily perturbed and once the bob leaves that position, it never returns there. It just goes down to the more stable equilibrium point. There are two equilibrium positions here, one corresponding to theta equal to 0, the other one corresponding to theta equal to pi. Okay, and you see that this is an unstable equilibrium point. And now the technique here is that when theta is small, you are able to expand this. What you are doing is you are expanding sin theta into a power series. Now you see that for small values of theta, sin theta is approximately nearly equal to theta. Okay, so this is generally the technique of handling nonlinear problems, and that's why we did a very elaborate study of this. Now we have to have a deeper consideration for this, because what is the error? See, we are going to approximate a nonlinear function. For example, the sort of equations that we have are something like this. Let us assume that P00 equal to 0. So 0, 0 is an equilibrium point. We assume that it is an isolated Now what one does is expand Pxy and Qxy in the neighborhood of 0, 0. Therefore, what do you get? Pxy can be written as some Ax plus By there are term. Qxy where you have the property that epsilon 1 divided by goes to 0 0, 0. Now this is the sort of error term that you have in this expansion. Then what one does is this: you, instead of looking at this given problem, you look at this problem. Now you see whether for this, of course 0, 0 is an equilibrium point, and if the, for certain approximations, now this is going to be again a isolated singular point, and then all our theory applies here for this system. The second, the deeper question that you have to ask is, how or is the behavior of 0, 0 as an equilibrium point of this, and its classifications are valid for the nonlinear case also. Now this needs deeper study. It has to do something to do with the order of the error term that you have. I stop with these comments at this stage, and now we introduce a new method by which we can analyze the nonlinear equations. So I think I'll pass on to the stability theory using Liapunov's direct method. We'll come to the theme of today's lecture. So we take up stability theory using what is called Liapunov's method. Now you see, Alexander Mikhailovich Liapunov was a Soviet mathematician who lived between 1857 and 1918, and I think his brief biography is available in, if you look into the book by Simmons on differential equations. I think you would have seen this. The reference to what I am doing next is the chapter 61 of Simmons. So I'll just give that reference to you, which you can look into. This is not discussed in Hurevich. That's why, however, I feel it is something very interesting. Okay. So we take up Liapunov's method. Liapunov is say A.M. Liapunov. He was a Russian mathematician of repute. And this method is due to him. And he uses a very simple intuitive idea picked from physical considerations. Now you see that suppose you have a dynamical system, and you see that the dynamical system, assume it is in equilibrium at some point. What you can say about is its total energy is that at least locally the total energy of the system is at a minimum, so that you need to push it away from that point. You have to apply more energy. Some external force is required, and unless, suppose there is the energy well or something called an energy sort of minimum energy in some neighborhood, means that the energy level at other points is more. So if you push it out, so it's a system like this. Suppose you look at a bowl kept like this, and there is a marble which is at equilibrium at that point. There the total energy of the system is minimum, at least locally, in comparison with what is happening here. So what happens is, if you apply force, what happens is it goes here. There the energy of the system is bigger than the energy of the system or the marble at that point. Therefore what happens is, there is a tendency for this to lose energy and come down to this equilibrium point. Now this is something observed in nature. Now this idea has been exploited or made use of by Liapumov to study the stability of the equilibrium points of a non-linear system. This now we are considering, what we are considering is not necessarily a linear system. So in certain cases it is applicable, not that it is universally applicable. It depends on your cleverness to find certain functions. Okay. So you look at chapter 61 of G.F. Simmons. That's a reference. Simmons, his book on differential equations and applications. Okay, right. Now this particular book is interesting because it gives the biographies of the mathematicians who have contributed to the development of the subject. So you see many people who have worked and contributed for the development of differential equations. Their brief biography is included. It's very interesting to read. It's a nice book. A lot of material is there. Okay, and it is very readable also. Okay, so the method consists of the following. So what we are looking at is a system I'm following the same notation as we were using in Simmons. He uses F and G. Okay. So this is the system that we look at. Assume 0, 0 is an isolated singular point. Or we can call it point. This is also called a critical point. See, another name for this is critical point. It's called, physicists call it the equilibrium point. Okay. Let C be a characteristic of 1. So there is some point x naught y naught, and x t naught is equal to x naught, y t naught equal to y naught, and then x t y t is a solution of the initial value problem. And what you have is that this is a representation for the particular characteristic. Now this is an autonomous system that we are looking at. Now what we do is, see, the idea that Liapumov uses is this. He introduces what is called an energy function, Exy. Okay, we will make the properties of this particular function what we are looking for. So let Exy be it's a real valued function defined on Pn. So this is xy belongs to certain d in R2. Okay, that is what I mean by the domain of E and Q. We assume E is a continuously differentiable function. And we also take E00 to be equal to 0. That's the nature of the function. So it's a continuously differentiable function defined on the domain of P and Q, and E00 is 0. Okay. Apart from that, so let us call this the energy function. This is called the Liapumov function. For the time being, borrowing a term from physics. Okay. Now what happens to okay, we also assume that EXY is in its domain. So EXY is greater than or equal to 0 at 0, 0, E is 0. Now look at, so we have the C. So along C, that is the characteristic. E xt yt is a function of t. For t greater than or equal to t naught, or defined on some interval. Now we are not very specific about it at this moment. So we call this et yt. Okay, right. Now compute the derivative of E with respect to t of this function. So d by dt of et is equal to this is equal to where p and q are the functions that appear in equation 1. Okay, so this is something very important for us. Okay, so we have now, you see, this is because along the characteristic xt yt you have dx by dt equal to p, dy by dt equal to q, and so we are substituting that. This is what you get. Okay, now how do you look at the behavior of the characteristic? You look at the behavior of the characteristic in the neighborhood of 0, 0 by looking at the behavior of et. Okay, so we of the equilibrium point by analyzing what happens Et as t becomes large. Okay, so now we make certain definitions. So before we use this method, we need certain definitions. The geometry is fascinating here, I will come to that. But before that, we'll make some definitions. It's a simple idea but profound idea that he uses, and geometry and dynamics go together to give the results. Okay. Make some definitions. Yes. Let E be a continuously differentiable function defined in the domain of E and Q. We assume zero. Now we make the following definitions. E is said to be positive definite if EXY is strictly positive whenever XY is at 0, 0, it is 0, 0. So at 0, 0, EXY is 0. Okay. Now an example of such a function is example look at this function to n. We assume a is positive, b is positive. Now you know that this is a smooth function and m and n are integer, positive integers. Then this is a positive definite function. We are taking a positive, b positive. You see that it's smooth. E0, 0 equal to 0, but nowhere else E is 0. So this is an example of a positive definite function. Now we define what is called first definition, second definition. E is negative definite. If for xy at 0, 0 it is 8. See, so it's the same example. So if E is positive definite, now you see that with A negative, B negative is a negative definite function. Okay, this is an example. This is a negative definite function. So A Z plus positive integers. Now we define two more functions, namely the third definition is exy positive semi-definite. If E00 equal to 0 and EXY greater than or equal to 0. In fact, this is included in that. E00 equal to 0 is included in that. So I think I can take it out. An example of such a function is define EXY to be equal to A x to the power 2n, where A is positive. Then what happens? See, in the xy plane, for all y, see x equal to 0, this is x, y. The value of the function on x equal to 0, that is the y axis, is 0. So the function, what you can say is that exy is greater than or equal to 0, but exy vanishes here. Okay, or this one. or this one. Where A is positive. All these are examples of semi-definite positive semi-definite functions. Likewise, okay, EXY is said to be negative semi-definite if EXY less than or equal to 0, and of course we take EXY equal to 0. We are interested only in that functions. We are interested in E00 equal to 0, definitely 0. I can put this because I don't want we are considering only functions of this kind. If EXY is less than or equal to 0, for every now you see that if remark minus EXY is negative and vice versa. Similarly, if EXY positive semi-definite now the difference between the positive definite function and the negative definite function, the positive semi-definite function is that EXY is 0 only at 0, 0 and elsewhere it is positive, right? In the case of positive semi-definite function, we allow the function to be 0 elsewhere also. But certainly the function is greater than or equal to 0. So you see that the condition is that this is greater than or equal to 0. Here the condition is less than or equal to 0. In the other case it was E greater than 0 except when xy is not equal to this, and EXY is less than 0, xy not equal to 0, 0, where of course it is EXY is assumed to be 0. So we have already looked at the examples. Now we use this. How do we use this function? So let us consider. Let function equal to 0. Then consider the equation for xy belonging to the domain of E. Then what do you have? Okay. So this is the x-axis, this is the y-axis, this is the origin, this is Z. Now if you look at the behavior of the function, so it's something like this. And that depends on the function, of course. In fact, the functions that we have defined here has this particular shape, something like a bowl. Okay, it's a sort of of what you call, it resembles a paraboloid. The graph of is a surface space which resembles a paraboloid. Certainly it stays in the upper half of the xyz space for z equal to z greater than 0, and what you have is that exy e0 0 equal to 0, therefore it passes to the point 0 0 0. The surface x equal to 0, y equal to 0, z equal to 0. And in fact the xy plane is tangent to at 0. So it stays above the xy plane, that is in the for z greater than or equal to 0, and it is 0 only at x equal to 0, y equal to 0. The z equal to 0 only at x equal to 0, y equal to 0. That's about that. Okay. Now we define what is a Liapumov function. A positive definite function Now I am assuming the smoothness that I have assumed it before. Exy with the property zero, and see, you recall this ET. What is ET? ET was E of xt yt. We are taking a characteristic. Then you see that the partial derivative of E with respect to x into dx by dt. Dx by dt is P plus Q. This is what we have seen. Okay. Now, such that this particular expression, that is dE by dx is negative semi-definite. If negative semi-definite is called a Liapumov so the properties are, it's a positive definite function exy with the property that dE by dx P plus dE by dy Q is negative semi-definite. Then this is called a Liapumov function. Now, what is the significance of this? We will see. Now, you see that, so let me denote this by, because this expression will be often recalled. Okay, I'll just wind up with the statement of a theorem. But before that, let me look at this. Some pictorial representation of this Liapumov function. So let us take the XYZ space. Then you have a bowl like this. This is the shape of the surface. Now, so this is Z is equal to, that means if you take a point 0 here, this point is corresponds to that is what you mean by the surface Z is equal to E of xy. Now we are assuming, okay, what happens to this? Suppose you have a characteristic here. Okay. Suppose this is xt by t. Then E of zt or if you want, you call this ET. For the t interval. So say for t greater than or equal to t naught. Then you see, corresponding to this, there is a curve here on the surface. Okay, so it is on the surface. So this is your ET. As t changes, t is some t interval, t naught. As t changes, you are here. This is t. So this is the point, this, and corresponding to that, there is this ET. So as t changes, you have a curve on this space. Now we look at the behavior of this particular curve, who on the Liapumov, the surface represented by the Liapumov function, and its behavior along a characteristic to understand the behavior of this characteristic. Now, if it's a Liapumov function, if E is a Liapumov function, we also have the condition 3. If E is a Liapumov function for 1, it is now, this is where it gets related to the equation 1. Then what we have is this. Semi-negative definite. That is along C you have dE by dt is, that is, E decreases, the value of E decreases. So see, you have a bowl like this. On that, the E value is the height of this. So when you move along the characteristic, what happens is the E value decreases. Therefore, when is that possible? That is possible only if the characteristic stays in the neighborhood of the equilibrium point. Now this is the whole idea. See, this says E decreases. This is the rate of change of E along the characteristic, and E decreases. So this says ET is decreasing, or at least it says not increasing. So what is the behavior of the characteristic? The behavior of the characteristic is that it goes near this, because we have chosen such a surface, and what we are demanding is that the E value evaluated at every point xt yt decreases as t increases. Okay, and that can happen only if the particular xt yt stays in the neighborhood of that. Okay, so the question that you have is, for, you see, this part does not talk about a specific characteristic. It only talks about the partial derivative of E with respect to x multiplied by P plus partial derivative of E with respect to y multiplied by Q, and we are demanding that this is semi-negative definite. Okay, therefore you see that the question that you ask is this: What is stability? This equilibrium point will be stable provided the characteristics, once it reaches a certain neighborhood of the equilibrium point, it will continue to stay in the neighborhood. So that is what you mean by the equilibrium. That is what you mean by the equilibrium point is stable. Okay, so and then we can say more about it. If this collapses to 0 0, the characteristic collapses to 0 0, then you say the characteristic actually approaches 0 0. In either case, now if this is the scenario, does not talk about a specific characteristic, and this particular condition would certainly assure you that all characteristics in the neighborhood, once it is in the neighborhood of 0 0, it will remain in the neighborhood of 0 0. Now this is the beauty of the argument. So the question that you have is this: given 1, is it possible to obtain a Liapumov function? And all that explanation that we have given is at the moment not a rigorous statement, but what we use heavily bank on the geometry and intuitive ideas, that we say that a characteristic would stay in the neighborhood provided its projection projection onto this Liapumov surface, that we call it the Liapumov surface, has a tendency that it goes down, okay, so that it stays closer to the origin. Okay, so once it is semi-definitive, I mean once it's a Liapumov function, you are assured that all characteristics around the equilibrium point 0 0 has the property that their projections will be just going down, that is the corresponding ET will be decreasing in value, so that the xt yt, and that is possible only when xt yt stays in the closer neighborhood of 0 0. Now I am in a position to state the main theorem. So what I do is that okay, let me state the main theorem and then conclude with that, and then we will prove the theorem in our next lecture. Okay. So let me make the statement of the theorem. So statement of the theorem corresponds to the question that I have raised here. Okay. So we have stability provided there is a Liapumov function. Okay. And you see that this actually, we will look at a physical example, and you will actually see that the Liapumov function in that particular physical problem, we have looked at the dynamical situation of a motion of a what you call a spring or simple harmonic motion. In all these cases, you will see that what you have is the Liapumov function turns out to be what is called the energy expression. Okay, so we will state the theorem. So I make a remark before that. The concept of Liapumov function is a generalization of the energy function. physicists infer that the equilibrium point is stable if the energy is minimum locally. It is in some neighborhood of that the energy is minimum, which amounts to, see, this is the energy function, which says the energy in the neighborhood of this equilibrium point remains or at the equilibrium point remains minimum. Okay, so that it is a minimum value, it takes a minimum value at the equilibrium point. Okay, so the same idea has been captured here and generalized by Liapumov and to study more general systems. Okay, so let me just make the statement of the theorem. This is the main theorem. If there exists Liapumov function Exy for the equation 1, then the corresponding critical points (0, 0) is stable. Is stable equilibrium. Now, if in additionally, further, if it is negative definite, if 3 is negative definite, 3 is we were talking about negative semi-definite. For a Liapumov function, it is sufficient to be a negative semi-definite. But if further it is more strong, like if the expression 3 that you have, this is the expression, is negative definite. This is the one that links E with the given system 1. Okay. Yes. That means the path eventually collapses to the equilibrium point. Okay, that means limit xt t tends to infinity xt by t goes to 0, 0. Okay, with this statement, let me conclude today, and then in my next lecture, I'll take up the proof of this theorem and look at some examples. Okay, thank you very much.